Okay, now we can generalize the Cauchy Schwarz inequality to generalize a square linear functional. This is given by the following theorem. Suppose we have a linear space and also we have a square linear functional to this, or could be mapped to the set of complex numbers. Let Q be the quadratic form induced by this A. We know that this means that Q of x is the square root of AXX. Okay. Suppose that this Q is positive definite. That is to say that the Qx is greater than or equal to 0, and that the Qx equals to 0 if and only if x is equal to 0. Then we have a similar Cauchy Schwarz inequality, which is that the Q of A of x y is less than or equal to the square root of Qx times Qy for any x and y in X. And the equality holds if and only if, I should say I put the absolute value here. The equality holds if and only if x and y are linearly independent. Oh, sorry, linearly dependent. That is to say that there exists lambda 1, lambda 2 in R, such that the lambda 1x plus lambda 2y is equal to 0. Okay, so this is actually the same as before. You can either say this, or you say that the equality holds if and only if x equals to 0 or y equals to 0, or there exists some constant lambda such as x is equal to lambda y. Okay, and if you want the equality holds, that's the only possible cases. Okay, so the proof, you can see that basically the okay, so without loss of generality, we assume that y is non-zero. Okay, I will only prove the real case. Here we'll assume this to be just real. Okay, now for any lambda in R, we know let's consider the Q of x plus lambda y, and by definition this should be the quadratic form of x plus lambda y. That will be just a of x plus lambda y, x plus lambda y. And this, by definition, we can just expand this. We have x, axx plus 2 lambda axy plus the lambda square ayy. And we know this is just the Q of x plus 2 lambda xy plus lambda squared qy. Okay, so let's say we call this lambda, we set this lambda to negative axy over qy. Then this becomes q of ax is the same, and here we'll have minus axy squared over qy, and here we'll have plus axy squared qy. We have 2 here, so now you have the qx minus axy squared over qy. Okay, and we know this is this q is a positive definite, so that means this is greater than or equal to 0. So that tells us that this is greater than or equal to 0. Okay. So we know that the axy square is less than or equal to qx times qy, which is the same as the axy absolute value is less than or equal to qx qy square root. Okay, so now let's see in which case this inequality becomes equality. Well, if it is equality, then we can see that we know that this q of x plus lambda y is equal to the q of x minus a. We know this is always true, and we know that this is equal to 0. Okay, so if this holds, that means the equality here holds, then that means this is equal to 0. And if this is equal to 0, that just means that this is equal to 0. And that also means this is 0, because the q is positive definite. So this is true if and only if x plus lambda y is equal to 0. Okay, so that is the case where the y is non-zero. Y is, if x is non-zero, then have something similar. If either one of x and y is 0, then apparently the inequality holds. Okay, so that's the proof. Okay. Suppose we have inner product space, then we define the norm induced by the inner product. Okay, then we show that this will be actually a norm. Okay. Okay, so we defined it in this way, but as we said, if we call this induced norm, then we actually need to show that this is indeed a norm if we define x in this way. Okay, so that's what we're going to do in this proof. You can see that to prove it is norm, we need to show that is positive definite, which is true since this is the inner product, and it's also homogeneous, and that's also easy to show if you have a lambda x, and according to the definition, this will be the lambda x square root, and according to the definition of inner product, this should be the lambda. Right, you need to pull out the lambda, and this square, and then x, and together you take the 1/2. I take the root, so that's why this is just that x, and this thing here is the norm. It's the norm. 1/2 here. This one is the norm, so it's indeed homogeneous. So the only key thing is to show that it satisfies the triangle inequality if we define the norm in this way. So let's show that. Okay, so we know that this, according to the definition, should be the inner product of x plus y with self. So we want to show, so we have this, and that is, when we expand this becomes xy plus yx plus yy, right? And you know that the first one is x squared, the second one is 2 times x, y. It's less than or equal to that because this is 2 times x, y, and by Cauchy Schwarz inequality, this is less than or equal to this, and then we have the y squared, and this is like the sum of these two and squared, and that shows the triangle inequality. Okay, and then we can also show that when we have inner product space, then the inner product is actually continuous with respect to both arguments. With respect to both arguments. So what that means is if you have xk goes to x and the yk goes to y, then the inner product of xk, yk goes to xy. So this is a general case. If you just have one sequence, say you have xk goes to x, and y stays the same, then you just have xk, y converge to xy. Okay, but if both are moving, that you still have this inequality. So this is even more general. Okay, so let's see how to prove this. You know, the idea here is to show that you take this difference, you try to show that this goes to 0 if xk goes to x and yk goes to y. Okay, and this is a very typical technique of this is you add something and you take it, you subtract it as well. And then just to split these two, every time you make one of them unchanged. So for example, this one, you're going to minus xky, and you add it back, and then you take the x, you take out the x, inner product of x and y. Then you use the triangle inequality. You have xk because of linearity of this inner product. You can split this, and also you have xk minus x y. And then by triangle inequality, you know this is less than or equal to xk and the yk minus y plus this is xk minus x and the y, right? By Cauchy Schwarz inequality. And now this one apparently goes to 0 because the y is fixed and xk goes to x. And here you need to be careful that because xk converges to x, so that means this one is bounded by some constant, say it's bounded by m. That is how you show that the whole thing is converging to 0, just because this first thing is still bounded by some constant. In general, it may not be true. If xk blows up, then the product of this may not be going to 0. But it's not the case here, since xk is convergent. So you actually need to show that this xk is a bounded sequence since it's convergent, and then you can show that both terms goes to 0. This is how you show that the inner product goes to this. Okay, so that's a common technique. Similar to the one that we used to show the product of two convergent sequence. If I make a component-wise product, you get a new sequence, xk, yk. You want to show that it's converged to xy if they are all numbers. Right? The technique is the same as we did in analysis. Okay. Now consider X as a inner product space. Okay, then X is strictly convex. Okay, so remember to show this by definition of strictly convex stats or space. We know that for any x and y with norm 1, if they're different, then we should have lambda x plus 1 minus lambda y. We should be able to show that this is less than 1, right? This is the definition. We want to show that this is less than 1, where x is equal to the norm of x is equal to the norm of y equals to 1, and x and y are different. Okay, so let's see how to show this. Let me square it first, so I can expand this. I'll break the square, then we have the lambda square. It's easy to show that. I'm going to show the details. So lambda, 1 minus lambda. Then if it's just a real Hilbert or inner product space, then we'll have just have x and y. Otherwise, we will have x, y, and then yx, and we add them together, there will be a real part of this, real part of x and y, inner product of x, y. Okay, I can still keep it. It doesn't matter. The proof is the same. Okay, then we have this. Okay, and this part, by definition, by the Cauchy Schwarz inequality, this is less than the product of the two norms, which is this. Then we also have the 1 minus lambda square y square. Okay, and now because this norm is equal to 1, these are equal to 1, this is equal to 1. So what do we have left? It's just the lambda square plus 2 lambda 1 minus lambda plus 1 minus lambda square. Okay, so you actually compute this. This is lambda square plus, say I combine the last two terms, it will be 2 lambda plus 1 minus lambda, 1 minus lambda, extract the common terms. And this part I know that is equal to 1 plus lambda. So the product of the last two, the parentheses terms should be lambda 1 minus lambda squared, and that's just equal to 1. Okay. Remember that x is not equal to y, and they both have norm 1, so that means they cannot be equal. They must be pointing to the different direction. That's why this one here shouldn't have less than, shouldn't have equality hold. It's not possible. It can only replaced by, we have to replace it by strict inequality, and that's why we have this strictly less than 1. Okay, so that's the argument here. From there to there, we cannot really get equality since x and y cannot be linearly dependent since we already have this. Okay. Now I'm going to give you a proposition. The question is, we know that when we have an inner product space, we can use the inner product to induce a norm. But you may wonder if we only have a norm linear space, we have a norm, or we have a B star space. It is possible to convert it into an inner product space. And here, this is a sufficient necessary condition to show that this is possible. So suppose we have x with the norm here, which is a B star space. It's a norm linear space. Then there exists an inner product such that it can be used to induce this norm. If and only if the following holds. called the parallelogram law, which says that the norm of x plus y squared plus the norm of x minus y squared must be equal to 2 times the norm of x squared plus the norm of y squared for any x and y in the space. So the norm must have this special structure such that this holds for any x and y. Then you will be able to find an inner product such that it is consistent or compatible with your norm. Okay, so I'll give you a very brief sketch of this, and I'll leave this as homework. You can practice yourself. So actually, one direction is pretty easy. For example, if you know that there is a norm, there is an inner product that can induce this norm, then you can just use that fact to show that this norm satisfies the parallelogram law here. So that's obvious. The other direction is quite tricky. So the idea is so what we know is that it satisfies this one, but how do we get this inner product? So there's only one way to get the inner product, which we define this way. It has to be equal to, so I say there are two possible cases. If it's a real B star space, then you can define your inner product to be this. It's minus y squared. Okay, and if it's a complex B star space, then you need to define the norm, inner product to be that instead. Okay, so this is the case where the k is the real numbers. This is the case where it's this. Okay, so the proof is based on the following facts. You try to prove that step 1, you try to prove that the x plus y z is equal to x. You know, if you want to prove this is an inner product, you need to show that it's linear in both terms, right? And if you have a scalar multiplied to one term, then the scalar can be pulled out, right? That's what we need to do. So let's say that we consider the simple case. Let's say just consider a real B star space. Then what you need to do is to show that this is true for any x and y and z in the space. Okay, so you need to play around with this identity here to show that this is true. Okay, so you know that right now you define this norm or this norm in this way. So and you're going to use the property of the norm here to show that this is actually true. That's the first step. Second step, because if you can show the first one, then it is easy to show that you have a 2x, not just 2x, say, for example. For the second step, you can also show that the x and y is equal to, if you have a negative on one of them, then it's the same as you put negative on the other, and it's the same as this. This is relatively easy to show. Okay, you just recall the definition here, for example. If you have a negative here, then that means you swap this by negative, and this by plus. So you just have x minus y equals to the minus of x and the y. Okay, similarly for the other. So this is easy. Then the step 3. If you have the first two steps, then you'll be able to show that this is true for any x and y, and n as an integer. And that's pretty easy to show based on the first two. Okay, essentially you just say, for example, you have this x-axis, this is y, it's just x, y, and then you have x, y here. So that's just a 2 times x, inner product of x and y. And you have this, and you can just do this for all the integers. Keep adding it, you get this. Okay, and the step 4 is to show that for any rational number, so you want to show that this is true. Okay, so that's not difficult to show. So that's one step you want to show. Then this shows that it works for all the rational numbers. You know, this is the rational number. And then finally, you show this linearity. For example, you want to show that the lambda x y is equal to the lambda times x y here. You want to show this. And to show that, you can think, so you have the lambda x y. Well, although we don't know this is exactly true on the right, but we can approximate this lambda by a rational number, let's say r. So we take the difference between this and r x y. And I know that this, I can put the r inside as we proved in step 4. So this will be rx y. And then according to the first step, we know this is just equal to the lambda minus r x y. And then by the Cauchy Schwarz inequality, we know this is equal to try to show that this is true. Okay, and then you see when r is getting closer to lambda, this goes to 0 on the right hand side. So this is the why we showed that it is also linear. Okay, so it's not really trivial, but it's feasible, it's doable. Okay, so now we have talked about all the properties of inner product space, and let's say that we want to talk about inner product space. If the inner product space is complete, then we call it a Hilbert space. As we said before, this is as an analog of normal linear space and the Banach space, or B star space and the B space. Okay, so definition for Hilbert space is actually just an inner product space which is complete. Okay, so that's the definition. So when we refer to Hilbert space, we just know that there is already an inner product defined, and the space is complete under the norm induced by the inner product. Okay, so a very famous result called the Pancreatic Inequality is actually defined for a special type of Hilbert space that we introduced before. So here, let's consider, let's say this is the open bounded set. Be an open bounded set in Rn. Okay, and we denote C naught k. These are all the continuous functions which vanish at the boundary of this omega. Okay, so what it says is that you have this is the omega. Okay, and it's 0 near the boundary means that for each point on the boundary, there is a small neighborhood, so that the function u is 0 there. Okay, it could be really small, small neighborhood, but 0 near the boundary. Okay, and apparently it will be 0 on the boundary. Okay, and then the following inequality holds for any u in C0k. There is, so on the left, we take all the multi-index less than k. It's less than or equal to some constant times the integral of omega d alpha ux squared dx. Okay, so what this means, the c, by the way, c equal to c k omega. So that means it only depends on this omega and k. It doesn't depend on u at all. It works for all the u in this C0k space. Okay, so what this inequality means, you look at the right hand side. This is the integral of the squared derivative of the highest order. So when you set this to be C0k, this is the highest order. Right? For example, if k equals to 2 and you have two variables, that means this will be d squared dx1 squared, or du squared dx1 dx2, or du squared dx2 squared. Right? We all the highest order of derivative you can take. And you take the sum of this, you can use this to bound all the lower, all the derivatives of lower orders. Okay, all the doesn't matter how large this k is. This equal to k will be able to bound everything that is less than k. That's what the Pancreatic inequality says. It's a very important inequality used in partial differential equations. Let's see, for this simple version here, we actually can prove it analytically. So how do we prove this? Remember that the omega is bounded, so that means we can enclose it into a big box. Okay, and say let's consider, without loss of generality, let's consider that this is included into this this box, or this hypercube. Okay, assuming that it's in the first quadrant. Okay, so now, because it is included in this box, which we, let's say we denote it by omega 1, then because u is in C0k omega, so I should then make it slightly more clear. So this is our omega. This is the big box. This is the omega. This is the omega 1, which is the hypercube. Okay, so the u is 0 right here. Okay, so we can continuously extend this. Since it's 0 already, and then we can just continue to expand them to be 0. So it will be 0 on here. It's actually 0 everywhere outside of omega. Right? So that's why when we consider the ux, we can think that we take the partial derivative with respect to x1 and then integrate it back. So it will be equal to u0 x2 xn. So this x here is x1 through xn. So I know this is true plus from 0 to x1, then you will have the partial derivative with respect to the x1, the u of t, x2 all the way to xn dt. Right, this is by fundamental theorem of calculus. Okay, but this term is equal to 0 since it's on the boundary. It's the boundary of the omega 1, so it's 0. And so I only have the second term, the integral term left. Okay, so now we can take the square, and then it is just the same as the square of this integral. Now remember that all the x2 through xn, they're fixed. Okay, and you know this is less than or equal to 0 to x1. Just take this inside. dt. And by Cauchy Schwarz inequality, we know this is less than or equal to the 0 to x1 1 dt square root. Well, sorry, we have the square. We have everything in here square. I don't have the square root anymore. I have this 0 to x1 d of dx1 u of t x2 all the way to xn dt. Right? And now remember that the x1, we actually have xi less than or equal to a greater than or equal to 0 because this is in the hypercube. So the first term is actually less than or equal to a. The second term, sorry, this is squared. The second term, we're taking the integral of some non-negative thing. So we take the integral of this is definitely less than taking integral of the whole interval from 0 to a. So now we have a dx1 u of t x1 x2 through xn dt squared, right? Okay, then we have this, and you can see that the integral doesn't depend on x1 at all because it's only partial derivative with respect to x1. But then we take the integral of this t, which is in the place of x1, from 0 to a. So this is already independent of t. It's already independent of x1. So we can take the integral one more time of this ux over the omega 1, which is the cube. And then I know this is less than or equal to, then remember that this a, I will take the integral. This integral over omega 1 is actually the, I can repeat what I have on the right hand side. ut x2 xn here. This squared dt. Remember that this is a function of x2 through xn only. Okay, and then we take the integral of this for dx1 dx2 all the way dxn. And the omega right here is nothing but, actually you take the 0 to a, 0 to a. So since this is a function of x2 through xn only, so when you take the integral with respect to x1 first, for this one, then I just need to, it's just a constant. So we just get a out of it. So this is actually just equal to a squared, and then 0 to a all the way to 0 to a. And again, this function here, I'm going to put it in here, and dx2 dx3 all the way to dxn. Right? And this will have a minus 1 of them. So that inside this, I actually have, I actually can replace this t by x1, but it's just a change of variable. It doesn't change what this one actually is. It's still independent of x1 itself. Okay, but I can put it back, and then the whole thing on the right hand side becomes just the omega 1 of this ddx1 u of x1 through xn dx1 dx2 all the way to dxn. This should be squared. Okay, so this shows that actually the integral of u squared is bounded by some constant, and apparently this constant a here that only depends on the size of this omega. Depends on how you choose, how large you want to choose this one, but it's independent of what u is. So it would be less than or equal to a squared times this. So that's the first order. Okay, and apparently you can do this for the others, and by doing this inductively, you can show the Pancreatic inequality. So the highest order will be able to control the integral of the highest order of the partial derivatives will be able to control all the lower ones. Okay, using a constant independent of the function u itself. Okay, so that's the idea. And this Pancreatic inequality also, since this one can be used to bound itself, right? Because this one can be used to bound itself, so you can put this as less than or equal to, it doesn't matter, because here we just need to put it as a c+1. Okay, but the point is right now, remember that when we were trying to define the norm for C0k, is that the norm is defined in this way. This thing is called the norm of u in this C0k space, or squared. Okay, and we know that when we take the closure of this, or take the completion of this space under this norm, we'll get the Hilbert space, H0k. And now in the H0k space, we have the same inequality like this. It's just that all these derivatives become weak derivatives. Okay, but this inequality still holds. Okay, so in other words, we can define the norm to be this sum for this less than equal to k, or we can just define the norm to be this to be the norm C0k. But this will be equivalent to the C0k norm, because this can be used to bound all the lower order terms. Since if you have the less than equal to here, then definitely this holds. But on the other hand, this is also greater than equal to the one you only take this equal to k, right? And that means these two norms are equivalent. So they have the equivalent norm defined for the H0k space. Okay? So that's the idea. Okay. Well, we have said this inner product, and the one important fact about inner product is that we can use this to define the angle between two vectors. Okay. The angle between two vectors x and y in the Hilbert space is defined by take the inner product and divided by the norm, and this is the cosine of the angle is equal to this, or the angle theta is defined to be arc cosine, or the inverse function of cosine of this thing. Okay. Apparently, this is only for that the x and the y are both non-zero. If one of them is 0, then you just say the angle is 0. Okay, because that's a trivial case, which is not important or interesting at all. So when both of them are non-zero, so you can define the angle in this way. So this is actually a generalization of the angle we learned in Euclidean space. Okay, so if the theta is equal to 0, then we know that this just means that the inner product of x to y is equal to 0. Then we say they are orthogonal. We say x and y are orthogonal. Okay, and if say we have a set M such that the x, y is equal to 0 for any y in M, then we say that the x is perpendicular to M, or is orthogonal to M. Okay, or we can say that x is in the M transpose, M perp, where, let me say that the M perp denote M perp to be all the x in the space such that x is perpendicular to M. Okay, so very geometrically speaking, say if M is a subspace, then the this is 0. This will be x. Okay, so it's perpendicular to any vector in M. Okay, but it's a generalization to the infinite dimensional space. Okay, so let's see talk about some properties of the of this. Suppose we have a inner product space X. Okay, suppose I have inner product space, and for this M is a non-empty subset of X. Non-empty subset of X. Then the following statements hold. The first one is if X is perpendicular to Y1, and also X is perpendicular or is orthogonal to Y2, then X is orthogonal to any linear combination of Y1 and Y2. Okay. Second is that if x equals to y plus z, and y is orthogonal to z, then the square norm of x is equal to the square norm of y plus the square norm of z. So you can again see this is a generalization of the right angles, the equal identity for right angles. Suppose we have x is perpendicular to y for all the y's, for all the yks, and the yk convert to y, then x is also orthogonal to the limit y. Say if x is orthogonal to M, then we know that x is perpendicular to the span of M. And finally, we show that the M perp is a closed linear subspace of X. Okay, so let's prove them one by one. I think the first one is easy to show, right? So you have inner product if this is equal to 0, this is also equal to 0, that just implies lambda 1 y1 plus lambda 2 y2, this will be equal to 0. Okay, that's easy to show. The second is, let's say we have x equals to y plus z, so this is the y plus z square, and we can expand this, it would be y squared plus like 2yz, right? yz plus zy plus z squared. But because y and z are perpendicular, so these two will be just 0. That's why you only have the y squared plus z squared. Okay. Third one is this is by continuity of the inner products. Say we have the x, yk. If yk convert to y, then this should convert to xy. Each one of this is 0, so that just means that this is equal to 0. And that means that x and y are orthogonal. Okay, if x is perpendicular to M, then x is perpendicular to the span of M. This, again, you know that is a span of M means that it's all the linear combination of vectors in M. So according to 1, you know this is always true. So for any y1, yn from M, we know the x is perpendicular to, say, the lambda I, I is from 1 to n. We know this is equal to 0. But this is the span. There are elements from the span, or all the elements in the span of M can be written in this way, right? A linear combination of that. That's the fourth one. The last one, we want to show that this is a closed linear subspace. So to show that it's closed, we just need to show that every sequence, if they have a convergent, if it's convergent, then the limit must be in the space. Okay. So now suppose xk belongs to M perp for any k, and xk goes to x, then for any y, we know, for any y in M, we know xk y goes to xy, right? Because xk goes to x, and the inner product is linear, is continuous in both arguments. But because if xk is in the M perp, that means this is equal to 0, since y is in M. And then again, this implies that this is equal to 0, which implies that x is in M perp. And that shows that M perp is actually closed. Okay, it's a closed. And this linear is easy to show, right? For example, you have lambda 1 x1 plus lambda 2 x2. If you take the inner product of this with y, where y is some arbitrary vector from M, then you know this is just a x1y plus lambda 2 x2y. And you know that both of them will be equal to 0, since x1, x2 are both in M perp. This is true for any y in M. And that just means that this is also in M perp. Okay, so this is the proof. Okay. So that's all about the some basic properties of inner products and the angles that we can use we can define using the definition or the concept of inner products. But another important property of our structure that inner products can induce to the space is that we can talk about the basis. Okay? We can talk about the basis. Like in Euclidean space, we have bases. In the general Hilbert space, we can also consider bases, but it's just that we may have infinite many bases. This could be infinite dimensional space right here. Okay, so let's give the definition. Suppose we have X. That is an inner product space. Okay, and this S is a collection of orthogonal, so okay, this E alpha. So this A here is the index set. So I have this E alpha. Alpha is the index that is from the index set. So it didn't specify what this A is. It could be finite, it could be infinite, could be countable, could be uncountable. Okay, but anyway, we have a bunch of these vectors in here. Then we can ask orthogonal if you take the inner product of E alpha with any other E alpha and with any other E alpha prime, this is equal to 0 for any alpha prime in A, and alpha is not equal to alpha prime. Okay, in this case we call that as orthogonal. If in addition that each E alpha has the norm 1, then it should be A, we write consistently, it should be A. Then we call as orthonormal set. And orthonormal so they are not just orthogonal to each other, but they are actually normalized. Okay. If the S perp is just 0, then we call S, it's called complete. Okay. This is the definition. If the S perp is 0, 0 is the only vector that can be perpendicular or taken in the product of the vector 0 and any vector x in S, you get 0. This is the only possible choice, then we call it complete. Okay. So now we are considering in which case a inner product space has a complete orthonormal set, because only having a normal orthonormal set, well, we can use them to span a linear subspace. But the question is, if we want to get a basis, we hope to represent any vector in X using the vectors in S. That means we want to have a basis. We want S to be a basis, so they can be used. So for any X, we can write them in terms of, say, A alpha, E alpha. Okay, where A alpha is a coefficient, E alpha is the term in the S. So if we can write any X in this way, we can hope that S has this property. That's what we hope for. Okay, so that's why we may wonder in which case we can get something complete, because we will eventually show that the S is complete if and only if S is the basis. Okay, S is the basis. That means that every X can be written in some in a linear combination of the elements in S. Then the question, as I said, the question is in which case this X has a complete orthonormal set. And the answer is this is a general property that for any inner product space, if you have an inner product defined, and this inner product space is not trivial, it's not 0, then we'll always be able to find a complete orthonormal set, like this S. Okay, and that's what we're going to show next. Okay, and to show that, we need to use the Zuelen's lemma. So I hope this is something that you have seen before, but I'm going to introduce the idea here. So Zuelen's lemma states that if you have a so it deals with a partially ordered set. So what do we mean by partially ordered? So let X be a partially ordered set. So it's a partially ordered set. means that you can define the order between two elements. Not every pair of elements, but for some pair of elements, you can define the order between them. Say, you can define order between some pair of elements in X. Okay, maybe for two given arbitrary elements, you cannot really compare them, which one is larger, which one is smaller. But if you can, then this order needs to satisfy the following two properties. Where the order satisfies the first called if A is less than or equal to B. This is how we define how we denote the order. It's that A is smaller than or equal to B, and also B is smaller than or equal to C. Then this implies that A is smaller than or equal to C. So if it's an order, and it must satisfy this property. The second is that a element is always can be compared with itself. A is always less than or equal to A for any A in the X. Okay, if the order satisfies this, and then we call this X a partially ordered set. Okay, and then let's consider a subset of X. Let's say E be a subset of X. Then U, which is the element in X, is called a upper bound of the E. If you pick up any element from E, you know it can show that it's less than or equal to U. Okay, this is the case we call the upper bound. Okay, and then we can call M, which is the element in X, a maximum or maximal element of X if X is less than or equal to M for any X in X. Okay, so now we have all the definitions set up. We have a partially ordered set where a order is defined such that the order satisfies the following these two properties or two conditions. Okay, and if for any subset E, we call U an upper bound of the set E if any element E X in the set E is bounded by this U. Okay, it's less than or equal to this U. And if M, we call M a maximum element if M is greater than or equal to any element in X. Okay, so this is all the setup. So it's pretty general, right? This is pretty abstract and general. And then the Zuhn's lemma says the following. So lemma by Zuhn. So this says that if we have a partially ordered set, then and any totally ordered, let me explain what this is later. The totally ordered subset has an upper bound then X has an has a maximal element. Okay, so the only thing that we didn't specify is what is a totally ordered set. So totally ordered set is a set in X such that for any two elements in E, either X is less than Y or Y is less than X. Okay, so in other words, all the elements in E, you can actually sort them up so that you can sort it from, you can list the smallest one at the beginning and then gradually increase. But for any elements in E, you actually can compare the order between any of them. So this is why we call this E a totally ordered set, but this X a partially ordered set, because not every pair of elements in X can be compared. But in a totally ordered set, any two elements can be compared. Okay. So what this Zuhn's lemma says that if you have partially ordered set and any totally ordered subset has an upper bound, then the X must have a maximum element. Okay, and then we're going to use this Zuhn's lemma to show that every inner product space has a complete orthonormal set. Suppose X is the inner product space. Let's say this X is non-trivial. It's not just a 0. Then X has a complete orthonormal set. Okay, so let's see how to prove this. We first consider make the collection of orthonormal sets. Say I have this, where E is an orthonormal set. Then we can see this set E here is a partially ordered set, because when we say that we define the order as inclusion, meaning that if I have this E1 and E2, then we say that E1 is less than or equal to E2. It means so E1 is less than or equal to E2 if E1 is included in 2. That means E1 has a bunch of orthonormal vectors, and the E2 has also has orthonormal vectors. The E1 is a subset of E2. Then we say that E1 is less than or equal to E2. This is how the order is defined. So apparently not every pair of sets in this collection can be compared, has an order defined, but we can define this anyway, right, in terms of inclusion. And now, suppose that's this E1, say E2. So we have this. This is a totally ordered set. Okay, the collection of them is a totally ordered set. Then we consider the union of this. Well, this means that everyone is a subset of the next one, and everyone contains only orthonormal sets. That means all the vectors in each set, all the vectors are orthogonal to each other, and they are unit vectors. The norms are 1. Okay, but this is a subset of that. Then we take the union of them. This is still an orthonormal set, and it includes everything in here. So that means this is the upper bound of this totally ordered set. Okay, so now we show that every we know that every totally ordered set has an upper bound, and apparently this one is inside E, inside this collection. So by the Zorn's lemma, there exists a maximum one, right? So by Zorn's lemma, there exists S, which is maximal in this family E. Okay? And then we can claim that this S must be complete. We first show the existence of such S, which is maximum in E, and we also show that this S is actually complete. Okay, recall that by definition of completeness, so that this perp of S is equal to 0, right? We just need to show that the perp of S is equal to 0. Well, here, if we want to show that S is not complete, proved by contradiction, then we know that S perp is not equal to 0. It's not equal to 0, that means there exists some X in S perp, but S is not 0. Okay, so it's in S perp means that you take any elements from S, you get this equal to 0 for any Y in S, right? So now we can consider the X and S. Definitely we can normalize this X, say assume we can take X or the X over the norm of X, just scale it. It doesn't change the property at all, but the X has a unit norm. The norm of X is equal to 1. All right, now let's consider the union of these two, which we call S prime. Then apparently this S prime is again an orthonormal set. So this is again in E. At the same time, S is in S prime. But S prime is not in S, since X is not an element in this S. If X is an element in S, then you will be able to have this equal to 0. But apparently this is equal to the norm of X squared should be greater than 0 when X is non-zero, which is a contradiction, right? So the X cannot be an S, so that means this S is actually a proper subset of S prime. So we actually can define this. Okay, and so that is a contradiction to that S is maximum, because this S prime is not really less than or equal to S. That's not true. That's why this is a contradiction to the fact that S is maximum, as we show here. And this shows that S must be complete.